In this last video of section 3.2, we're going to take a look at some very useful formulas. These formulas are going to be ones that are going to be really great to actually kind of have dedicated to memory so that if and when they arise, we don't have to spend the excess time required to go ahead and actually derive them. Now, in the box here that I have at the beginning, you'll see that I have an integral of tangent of x. And you may recall from Calc 1 that that was going to be equal to a negative natural log of the cosine, or absolute value of the cosine. Or, if you were to go ahead and use properties of logarithms, you could take that -1 and bring it up as a power on the cosine, right? And so cosine to the negative first, that would turn into secant. Notice I'm not doing inverse cosine, but I'm doing cosine to the negative first. Now, it may be totally the case that you don't recall this, or you didn't dedicate this to memory in Calc 1. And if that's the case, you might be able to just quickly go ahead and refresh on why this is true by just double checking for yourself that if you were to do a u substitution with the tangent in the form of sine over cosine, you could generate this result. Specifically, if you let u be equal to the cosine of x, and therefore du equal to negative sine x dx. So I'll leave that for you to go ahead and check or verify again on your own. But again, this is something that's very convenient to have dedicated to memory. So that way, if it arises, you could just immediately state what the antiderivative of the tangent function is. Now, in a very similar sort of way, I'm going to ask us to now consider an integral for secant of x. Now again, this right here is not anything that we learned as a derivative rule in Calc 1. That is, there's nothing I take the derivative of in Calc 1 that generates for me just the secant. No memorized rule gave us just this answer. So trying to integrate this is going to be a little bit difficult to do. Notice that none of the other integration techniques that we've developed so far in Calc 2 are really going to be useful for trying to go ahead and work with this either. Integration by parts is going to be difficult, and it's also going to be difficult to do anything with trig identities because we don't have any nice trig identities for this. So I'm going to go ahead here and actually just perform a little bit of algebra. And this algebra at first can seem a bit strange. What I'm going to do here is I'm going to multiply by a fancy version of the number 1. And I'm going to choose to multiply by secant of x plus tangent x, and then a secant x plus tangent x. So since those are being divided, I'm just multiplying by 1. I haven't really changed what I'm integrating here, just changed the way that it looks. Now, of course, since I can imagine this secant of x as being over 1, I can take that secant and I can distribute it through the top. And so this would turn into a secant squared of x plus a secant x tangent x all over secant x plus tangent x. And it looks like I've taken something that's actually really simple with just a secant and I've made it ridiculously complicated. Well, it's actually really good news because this, while it appears complicated, is very, very nice. If I look at the denominator and the numerator and try to find a relationship between them, you might be able to see if I was to take the derivative of secant, I get secant tangent. And if I take the derivative of tangent, I get secant squared. That is, the numerator is the derivative of the denominator. Well, that makes it a perfect candidate then to perform a u substitution with. I'm going to go ahead and let u be equal to that denominator. But then that gives me that du is again going to be equal to secant x tangent x plus tangent squared x dx. And since I have all of that, I can then go ahead and replace what I have with just one du and a u. Of course, what this means is that my antiderivative is natural log, don't forget, absolute value of u plus c. Replacing u with what it's equal to, if u was a secant x plus tangent of x, I now have a antiderivative rule for the secant. This is so important, I'm going to go ahead and rewrite it again in its own box, and we'll see that this is, again, going to be a nice antiderivative rule to dedicate to memory, so that way we don't have to try to recreate this very strange process that we saw up here of multiplying by this fancy blue 1. A very, very surprising thing here to kind of force this u substitution out. But it's awesome, and it really helps us deal with this simple function that has a very difficult antiderivative. So now let's take a look at example number 6. Here I'm asked to find antiderivative of secant to the third. Now, very interestingly, we'll notice that what we had looked at in the past couple videos about integrals with secants and tangents in it is that I'm going to be in a little bit of a dilemma here. Let me just write out some scratch work that I'll erase again in a moment. But notice that if I tried the approach of saving a secant squared on the side, I'm not really going to be able to force out a u substitution because I won't be able to turn this secant into a tangent, or the secant of x into stuff with tangents of x. Notice that I also can't separate things out the other way by saving a secant tangent because I have no tangents. So kind of automatically, I'm not really going to be able to use trig identities to really help with this. Well, I could start going down that list that we saw at the start of this section and at the start of last section. Like, okay, is this a derivative rule maybe that I just memorized in Calc 1? Well, no, that's not true. I might be able to do some algebra to rewrite this, like maybe separating it into a secant times a secant squared. I mean, that's possible, but not really sure what to do with that. We could try a u substitution, but I don't see how that would work. And I guess the only other option that maybe we have here is maybe I could try an integration by parts. Well, let's take a look at this. This is kind of really strange. So I'm going to go ahead and I'm going to rewrite my integral here by breaking it apart into a secant of x and a secant squared of x. And when I do this, I might notice that this portion over here in green could be treated as my u. This portion over here could be treated as a dv. It's easy to find an antiderivative of. So I'll state here, using integration by parts, we'll let u be equal to a secant of x. dv would then be equal to my secant squared of x dx. That, of course, gives me du is secant x tangent x dx, and v would just be tangent x. So that would mean that if I continued my equal sign coming down, say by integration by parts, I end up with, start with u times v. So let's see, that's secant of x tangent of x minus the integral of v du. All right, so let's see, that's tangent of x times secant tangent. I'm going to make this secant x tangent squared x dx. Oh gosh, remember the goal here with integration by parts would often be to make this second integral here look a bit easier, but that doesn't look much easier at all. Okay, well, we could restart. Is this a derivative rule that I know from Calc 1? Well, no. Any algebra I can do to make it simpler? Maybe. It's not super easy to see how that might work. We could try to do a u substitution. Let's see, so if u is a tangent, then I need to have a secant squared. It doesn't seem like that might work. We could try another integration by parts. I'll hold off on that. Any trig identities I can use here? Well, actually, I'm going to go ahead and attempt to use a trig identity here. remember that tangent squared is going to be equivalent to a secant squared minus a 1. Now if I kind of simplify this all the way down, I'll see here that what I'm really left with is a secant x tangent x, and I'm going to have minus an integral of, and if I distribute through, I'm going to have a secant cubed of x minus a secant of x. Now I'm going to go ahead here and do one final Calc 1 simplification. Remember, I can separate this one integral into two integrals. Totally possible to do that. But notice each one of those integrals is going to need to be subtracted, right? Because I'm subtracting both of these. So notice that's going to give me minus an integral of a secant cubed of x, and then minus a negative integral of secant x. Okay, well, as long as I can integrate these two pieces, everything's good to go. Oh, and wait a minute. Notice what I have up here in the box. I have my secant of x integral, and we already found what that is. So that's very, very convenient. It's going to give me secant of x, tangent of x, minus integral of secant cubed. Here I can put in that natural log, absolute value, secant x plus tangent x plus c. Okay, so that's perfect. But what the heck do I do with this integral of secant cubed? Can you spot it? Well, you might notice. Wait, isn't that the integral we started with? In fact, if I was to kind of carry this all the way down, isn't that what this is equal to right now? So wait, I have again the case of the unknown integral. I could go ahead and state that if I added this to the other side, I would get two of those secant cubed integrals. And then that would just be equal to, on the other side, my secant x tan x plus my natural log. Right? And then I could go ahead and simply multiply both sides by a half, and I would have actually solved for my secant cubed. This shows us that it's very important to see that these different integration techniques aren't isolated, that they can overlap. That there may be problems where I'm going to use something like integration by parts and trig identities, maybe a U sub, and they might all happen at the same time. While that makes problems a lot more complex, it just means that I have to be a little bit more careful as I work through problems, and I don't eliminate options too quickly. With practice, you'll get much better at evaluating these, and of course you can use the worksheet problems to help you practice.